Because the rumor isn't enough, we need the ledger. The zone of avoidance problem. So we walk right into the blindfold. The zone of avoidance sounds dramatic, but it's just the plane of our own galaxy being a pain. Dust grains in the Milky Way scatter and absorb optical light. Stars crowd the field. Standard galaxy surveys in visible wavelengths hit this belt and go, nope, can't see. For decades, that stripe carved out 20% of the sky, exactly where our flow vector threads through. If you tried to chart mass there with optical catalogs, you were drawing a coastline through fog. Astronomers hate blank spaces, so they switched the light. X-rays don't care about dust the same way. Galaxy clusters trap hot gas at tens of millions of degrees, and that gas shines in X-rays. The CIZA project clusters in the zone of avoidance went fishing there. And get this, it started hauling up real catches. Bright, extended X-ray sources that matched the shapes and sizes of bona fide clusters, including the Norma cluster sitting almost dead in the lane. Suddenly, the maybe behind the Milky Way turned into there it is. Radio helped even more. Neutral hydrogen emits at a 21-centimeter wavelength, and radio waves slice through dust like it's not even there. With instruments like MeerKAT, people scanned those hidden latitudes and pulled out thousands of galaxies by their hydrogen line. Each detection gave a redshift, a position, a bead on a filament. Add them up, and you begin to see walls and threads where the optical sky showed nothing but star soup. The Centaurus wall kept going. Vela showed up as a serious player. Norma didn't look lonely anymore. Here's where it gets messy. These are not clean, uniform surveys. X-ray selection favors hot, massive clusters. Radio selection favors gas-rich spirals. You're sampling different kinds of structures with different biases, and you're doing it in a crowded field where galactic emission can contaminate your signal. So yes, the blindfold slipped, but it didn't fall off. We got partial, noisy windows. Enough to say hidden structure lives here, not enough to write the full mass ledger in pen. And selection bias does a quiet number on your maps. If your catalog is missing quenched galaxies because they've blown out their gas, your radio view undercounts dense cores. If your X-ray threshold misses cooler groups, your hot map overemphasizes the deepest wells. Combine that with uneven sky coverage, and you can warp the inferred density field without noticing. That matters when you invert motions into mass. The math is sensitive to holes. So teams started cross-checking. Take the galaxy's radio finds, follow up in infrared where dust is kinder, get distances with Tully. Fisher so you have peculiar velocities, not just redshifts. Fold in CIZA clusters from the X-ray side. Then run a Wiener filter on the joint velocity field. The picture that pops out is consistent with what the new eyes suggest. A crowded gravitational basin near Norma and Centaurus, threaded by filaments running right under the Milky Way's glare. The streamlines we saw earlier weren't guessing. They were sniffing what the optical sky hid. Now, uncertainty isn't just a data quality footnote. It's a system-level blind spot. The zone of avoidance sits exactly where geometry makes the reconstruction hardest. Distances along our line of motion amplify small errors. Foregrounds vary. Even our own sun's motion projects differently depending on latitude. That's why people keep saying caution in papers while headlines scream monster. The monster is our ignorance profile as much as any cluster. Still, patterns survive the caveats. The Norma cluster shows up in X-ray as a hot, dense node. MeerKAT's 21-centimeter surveys stitch a Centaurus Norma corridor. The Vela region, once a whisper, emerges as a supercluster scale over density, and on larger slices, hints of the Shapley direction peek through as the flow field leans that way. None of this erases the bulk flow number we started with. It grounds it. It says the pole line is real, and the hidden scaffolding is finally stepping into view. So what do we do with that? We reframe Great Attractor from a spooky noun into a working map. Not a single object, not a black hole, but a region of enhanced mass density we were blind to in optical light, confirmed by X-ray hot gas and radio hydrogen. We accept that catalogs are incomplete and build models that respect those gaps. And we stop pretending the zone of avoidance is a footnote. It's the test we have to pass. Next, we nail down what that name actually means, what the Great Attractor is, and what it is. Naming the phantom, what Great Attractor is and isn't. So let's say the quiet part out loud. Great Attractor was a flag, not a finding. The term showed up as people in the 1980s tried to explain why the local universe seemed to be flowing toward Hydra, Centaurus, faster than nearby masses could justify. It was shorthand for something big is yanking us in that direction. Useful at the time. But the name makes you picture a single monster. That picture is wrong. Here, S what it is as far as the data go. It's a region of enhanced mass density, a basin roughly in the Norma, Centaurus neighborhood, buried under the Milky Way's dust. X-ray maps like the CIZA survey light up hot gas there. Radio H, I work with MeerKAT threads galaxies under the glare. Peculiar velocity reconstructions, like cosmic flows with Wiener filtering, show streamlines converging into that basin. If you want a cluster as an anchor, the Norma cluster sits right in the mix. But the attractor is not one cluster. It's a patch of the gravitational landscape with multiple ridges and valleys feeding it. What it isn't, a black hole, a cosmic drain, or a single object that can swallow the Milky Way. Gravity doesn't work that way on these scales. We're talking about the combined pull from many clusters and filaments. Think of a watershed, not a plug hole. Water doesn't rush to a single point. It funnels through a network into lower ground. In our case, galaxies slide along filaments toward lower gravitational potential. That's the attractor. Now here, S where misnaming bites. Say Great Attractor and people stop at Norma, but the flow field doesn't. On larger scales, the slope keeps dropping toward the Shapley Supercluster, a far richer concentration of clusters around 650 million light-years out. Reconstructions consistently show that beyond the local basin, streamlines bend toward Shapley. Some recent analyses even argue the greatest attractor in our sky is Shapley on those scales, with the Norma region acting more like the throat of our local basin, the on-ramp into the longer downhill. There's another piece that helps clear the fog. Models that use the velocity field itself to classify the web. The V-web, built from the velocity shear tensor, tags space into voids, walls, filaments, and nodes based on how flows compress or stretch. In that language, the so-called Great Attractor region is a node fed by filaments like the Centaurus wall, with compressive directions along the three axes. The Milky Way sits on a filament flowing into that node. Past it, the compressive pattern lines up with Shapley's deeper well. That's a map in the language of motion, not just galaxy counts. You'll hear two families of models used to explain our drift. One says, look, a nearby overdense basin near Norma, Centaurus sets most of the local pull. The other says, sure, but the far field from Shapley dominates the big vector, the local basin just channels it. A third twist adds voids. The Dipole Repeller, an underdense region roughly opposite the Shapley side, pushes us by letting expansion run faster there. Away from the repeller toward the attractor, push plus pull. None of these require a single hidden monster. All of them are gravity plus structure, summed over scale. So why keep the name at all? Because it marks a real, testable place in the flow. Say Great Attractor region, and observers know you mean the basin around Norma and Centaurus that many flow lines enter. It's a working label like Virgo cluster or local void. But we should retire the folklore that treats it as a unique object with mythical power. It's one hand on the rope. And the stakes here are semantic but serious. Metaphors steer models. Call it a single attractor and you bias catalog building, lensing searches, even the way you align simulations. You might overfit local infall and underweight the far slope. You might miss that the cosmic microwave background dipole, our 630 kilometers per second relative to that radiation frame, is an integrated story. Nearby basins, far nodes, and underdensities all adding vectors. And the mystery isn't settled. If Shapley's mass is higher than we think, that long slope sharpens. If the local basin hides more behind the plane, the throat deepens. That's why we keep the question open. One last thing. People ask if this means expansion is broken. No. Inside bound or soon-to-be-bound regions, gravity wins and structures grow. Outside, dark energy stretches the web. The picture that pops out, matter draining off walls into filaments, then into nodes, can look like an inhale. That metaphor is fine if you keep it grounded. We're not reversing expansion. We're watching hierarchy within it. The V-web language keeps us honest. 3-axis compression at nodes inhale, 2-axis along filaments, 1-axis at walls, and 3-axis expansion in voids exhale. So, Great Attractor, a real basin near Norma, Centaurus, not a monster, a waypoint in a longer fall that likely aims toward Shapley, a label that helps if you use it carefully. With that cleaned up, we can widen the frame and see how our whole neighborhood, Laniakea, is stitched together by those same flow lines. The Laniakea Trap, our supercluster's drainage map. So here's where the picture widens and honestly clicks. Instead of asking what object pulls us, ask what river are we in? In 2014, a team used thousands of galaxy distances and peculiar velocities to draw streamlines, not dots on a sky map, but arrows showing how galaxies move. They outlined a basin they called Laniakea, immense heaven. We live inside it. Think of a drainage map. Rain falls on hills, finds tiny rills, joins creeks, then rivers, and finally a sea. Space does a version of that, except the rain is galaxies, and the hills and valleys are the gravitational potential. The V-web, which classifies space by how flows compress or stretch, gives you the scaffolding. Voids push out, walls guide sideways, filaments funnel in, nodes collect. Laniakea is the catchment. Its boundaries aren't drawn by galaxy counts, they're traced by which way things move. Follow the lines from our spot. The Milky Way sits on a filament. That filament runs toward the Norma, Centaurus region, the same neighborhood we've been circling. This is the Great Attractor zone in practical terms, the throat where streams converge. Inflow from the Pavo Indus filament from along the Centaurus wall, from scattered groups out past Virgo, they all sink toward that basin floor. Once you're in a basin like that, exits thin out. The flow directions lock in. But here's the twist. Those same streamlines don't die at Norma, many bend onward. On larger scales, they tip toward the Shapley Supercluster, a massive nest of clusters far beyond. So locally, Laniakea is the trap. Globally, the slope keeps dropping. That's why the old name misleads. Great Attractor feels like the end. It's a midpoint, the throat, not the ocean. The trap isn't doom. It's just dynamics. Inside the basin, gravity cancels the general expansion more effectively. Bound structures trade energy and merge. Groups fall into clusters. Clusters knit tighter cores. Outside, where the density is lower, dark energy stretches the metric and flows thin. That contrast makes the boundaries of Laniakea meaningful. They're the ridgelines where a droplet, a galaxy, would have flowed a different way if it started a few megaparsecs over. What sets those ridgelines? Under the visible, dark matter does. Cold dark matter built the initial skeleton. Baryons, the normal stuff, settled on top. We see the filaments because gas and stars light them, but the lines were carved by the dark first. The velocity field we measure today is a living echo of that scaffolding. When you integrate thousands of distances, Tully, Fisher, supernovae, surface brightness fluctuations, and invert to a potential with tools like Wiener filtering, you're not guessing. You're reading the riverbed. So why call it a trap? Because once flows drop through the throat, the gradient points one way. You don't get circular orbits at these scales. You get sliding. Our local group, Virgo, the Centaurus clusters, they share that vector bias. You can add the push from the Dipole Repeller on the far side, which helps tilt the field away from a big underdensity, but the net remains. Into the basin, then on toward deeper structure. And that deeper structure matters. If Shapley dominates on the long scales, then Laniakea's basin is nested inside a larger gradient. Picture a valley feeding a larger valley that runs to the sea. If you live on the small slopes, the nearest floor is everything. It sets your streams, your roads, your weather. Step back and you see that floor tilts again. joining an even bigger runout. Both views are true, depending on the map you need. Here's the practical payoff. Flow-defined superclusters like Laniakea let us build better distance corrections. When you know the local current, you can peel it off redshifts to get cleaner Hubble flow. That sharpens everything. The local value of the expansion rate, tests of homogeneity, weak lensing calibrations. It also means our fate in the cosmic sense is directional, not a date on a calendar, a corridor in phase space we already occupy. So the Laniakea trap isn't a cage, it's a path. We are midstream. The Norma Centaurus throat gathers us and our neighbors because the potential drops that way. Past that, the grade keeps falling towards Shapley. That's the river we live in. And once you see it as a drainage map, the inhalation metaphor stops sounding mystical and starts sounding like what gravity does inside an expanding world. It gathers. It takes the slack out of the web. It pulls breath inward along the lines already carved, reconstructing the invisible from velocities to mass. So how do you weigh something you can't see? You watch how it moves other things. That's the entire trick here. We start with distances, real independent distances, because redshift alone mixes expansion with motion. Tully, Fisher gives you a handle for spiral galaxies. Rotation speed ties to luminosity, so you can estimate how far they actually are. Type Ia supernovae are better when you get them, standardizable candles that pin distances tight. Add surface brightness fluctuations for nearby ellipticals, and you've got a ladder with rungs across the local universe. Now you compare. Hubble's law says recessional velocity should be h times distance. Subtract that should be from the observed redshift velocity, and what's left is the peculiar velocity, the extra due to gravity. Do that for thousands of galaxies and a pattern of arrows appears. But raw arrows are noisy. Galaxies have their own jitters, errors creep in, so we don't just eyeball it. We feed the velocities into a Wiener filter, a method that balances what the data say with what a sensible, smooth field should look like, given the noise. It's conservative. It won't invent wild swings just to fit outliers. Out of that comes a velocity field you can integrate. And because in linear theory the peculiar velocity field is the gradient of a potential, you can invert it to get the underlying gravitational potential, the hills and valleys sculpted by mass. That's the from velocities to mass leap. Not a guess. A causal step. Flows point down potential gradients, therefore the gradients map the mass field. In V-Web language, 3-axis compression at nodes is your inhale. 2-axis along filaments is guided flow. 1-axis at walls is sheet drain. And 3-axis expansion in voids is the exhale. What shows up is exactly the terrain we've been feeling. Near us, a deepening well in the Norma Centaurus neighborhood. Streamlines funnel along the Centaurus wall and Pavo Indus into that basin. You can overlay the CIZA X-ray clusters, hot gas lighting up the deepest pockets, and it clicks. Drop the MeerKAT 21-centimeter detections on top, and filaments hiding in the zone of avoidance snap into the picture. Independent tracers, same geography. But here's the kicker. When you extend the reconstruction farther, adding cosmic flows catalogs, new Wallaby and fast HI detections, folding in supernova distances where we have them, the streamlines don't terminate at Norma. They curve. They bend toward the Shapley Concentration. On those larger scales, the potential keeps dropping in that direction. The far field matters. The local basin remains real, but the slope beyond it is steeper still. Here's the scale paradox in plain view. Locally, velocities feel very non-Hubble strong inhalation into the Norma, Centaurus throat, tight convergence, obvious structure. Step out to hundreds of millions of light years, and Hubble's smooth expansion should wash over the noise. Yet the mean direction keeps leaning toward Shapley, and coherence hangs on across big volumes. Local maps say basin throat. Far-field mass says downhill keeps going. Both are true, and putting them together is the whole point. That's where the reversal lands. The greatest attractor isn't the close one. Shapley dominates on the big canvas. Our 630 kilometers per second relative to the CMB isn't a one-node story. It's a vector sum across nested scales. Nearby overdensities pull. The Dipole Repeller underdensity behind us lets expansion push, and the Shapley Supercluster's mass tugs the entire region, tilting the field we swim in. You can test this with predictions. If Norma alone drove the show, flow angles would converge tight on that node and die off beyond. Instead, velocity reconstructions show coherence across hundreds of megaparsecs, with angles gradually leaning Shapley-ward. X-ray maps find rich clusters in that distant direction. Weak lensing and cluster counts back up that Shapley is a heavyweight. The pieces fit a multi-scale pull, not a single throat pretending to be a drain. The methods keep tightening. Each distance you add reduces the noise in the Wiener filter and sharpens the potential. Gaia improves calibrations for standard candles. Daisy, Wallaby, and Fast feed more galaxies into the velocity net. The latest CF efforts show cleaner basin boundaries, more spherical shapes where appropriate, and a clearer separation between the Great Attractor region and other giants like Coma. Vela, once a rumor behind dust, steps out as a real supercluster scale feature. These are not cosmetic updates, they shift the weight on the map. There's a humility check baked in. The zone of avoidance still hurts. Selection biases still lean on the field. But the broad strokes survive every new pass. A node near Norma, a corridor through Centaurus, a farward bend toward Shapley, and a shove away from a large underdensity on the opposite side. If you drew a single arrow for our fate, it would start on our filament, dive through the local basin throat, then keep sliding down the long slope. So no, the universe isn't reversing expansion. This is hierarchy within expansion. Gravity corrals flows into wells carved by dark matter. Dark energy stretches the spaces between those corrals. When you look at it through the velocity field, not just where galaxies are, but where they're going, the inhalation picture looks less like poetry and more like plumbing. Matter drains, voids exhale, nodes thicken. We're in mid-current and now we can finally see the riverbed. Is the universe breathing, or are we falling? So here's where it gets interesting. We've traced the streamlines, weighed the basins, and watched our arrow bend toward Shapley. Now the question hanging in the air is simple and slippery. Is the universe breathing in, or are we just falling down a slope? Start with the clean split. On the largest scales, space expands. That's Hubble's law, backed by supernovae, by the CMB, by everything that sets the background. But on smaller scales, gravity doesn't care about that smooth stretch. If enough matter piles up, it carves a valley in the gravitational potential. Inside that valley, flows run downhill. Expansion still happens globally, but locally, motion is dominated by the slope. So yes, you can have collapse inside expansion. Both are true at once. The inhalation metaphor comes from the pattern that falls out of that split, and it's nailed down by the V-Web model. Look at a V-Web map. It sorts space by the velocity shear field into voids, walls, filaments, and nodes. In voids, flows stretch apart along all three axes. That's your exhale. At walls, one axis compresses while two stretch. Matter leaves the sheet. In filaments, two axes compress. Matter gets funneled along the pipe. At nodes, all three axes compress. That's your inhale. It's not poetry. It's the sign of the eigenvalues of the shear tensor. The field is literally converging. And you can see it in data, not just in theory. Voids empty out over time. Surveys show fewer galaxies per unit volume there as structure grows. Walls thin, filaments sharpen, clusters fat. Peculiar velocities point off high ground into troughs. Radio HI maps trace gas sliding along hidden filaments under the Milky Way's dust. X-ray maps show hot, heavy clusters at the convergent ends. When you step back and watch the whole pattern, it looks like breath. Out from emptiness, in toward mass. Exactly what the V-Web predicts when eigenvalues flip sign from stretch to squeeze. But hold on, the risk with metaphors is they smuggle in claims you didn't mean. Breathing can make people think the expansion itself is oscillating, like a cosmic chest rising and falling. That's not what's happening. The scale factor keeps increasing. There's no global inhale in the sense of reversal. Dark energy, whatever its true nature, is making that expansion accelerate on large scales. The inhale we're talking about is local and hierarchical. It's gravity winning regional skirmishes, while the wider battlefield drifts apart. So are we falling? Yes. Along our filament into the Norma Centaurus Basin and likely onward down the long slope toward Shapley. Falling here doesn't mean doom. It means sliding along geodesics in a curved potential. Bound systems inside those basins decouple from the Hubble flow. They merge, virialize, settle. The Milky Way and Andromeda are already on that path. Clusters in the basin will tighten while the space between basins stretches thinner and colder. Here's a clean way to picture the coexistence. Imagine a river delta on a rising tide. The tide lifts everything slowly, that's expansion. But channels still carry water toward the sea, that's gravitational infall. If you're a leaf in a channel, your motion is mostly the current. If you're between channels, you drift with the tide. Both motions add. Our peculiar velocity is the channel.